Welcome back. Today I'd like to talk a little bit about limits and continuity and higher dimensions. So I want to start with a definition. So definition, we say that a function f of xy approaches let's see. The limit L as the point xy approaches some specific point x sub 0, y sub 0, and write that the limit as x comma y approaches x sub 0, y sub 0 of f of x comma y equals L if for every number epsilon that's bigger than 0, there exists a number delta greater than 0 such that for all xy in the domain D of f, we have, and I need to go to another page here, we have that the absolute value of f of x y minus L is less than epsilon whenever 0 is less than the square root of x minus x0 squared plus y minus y0 squared is less than delta. Okay, so you can look back over that definition a couple times if you need to, but it's saying something sort of simple, and that is what does it mean for the distance between xy and x0, y0 to get close together? If it's close together, then this number is getting small. And it's saying that if you get this number small enough, in other words, if you get the point xy and x0, y0 close enough to each other, so let's say we have a point here, xy, and we have another point here, let's call this x0, y0, and let's say that we know that those 2 points, this is a circle around xy, and I know that that, let's say, has radius delta. Okay, so if I know that this point x0, y0 is within delta of xy, then I'm guaranteed that the function is close to the limit value. In other words, the functional value of this point xy is close to L. This is exactly the same as what our limit is in 2 dimensions, but now we're dealing with an extra dimension that this original point can live in. So if we know that x0, y0 is close to xy, then we know that also the functional value is getting close to the limit value. And that's what we say it means for a function to have a limit L. Okay, now that we know that, let's talk about some of the properties of limits when we're dealing with an extra dimension. So this is a theorem, properties of limits. And we're going to start with the limit as xy approaches x0, y0 of f of xy. Let's call this capital M, and the limit as xy approaches x0, y0 of f of xy. Let's call that L. Oh, I'm sorry. I made a mistake here. Let me rewrite. Of g of x comma y. Let's call that L. Okay, so then we get some properties. And the first property that we have is, what if we're taking the limit as xy approaches x0, y0 of f of xy plus g of xy. Well, it looks exactly like limits do in 2 dimensions. We can just distribute that limit across this sum and take the limit of each one individually, and then we get M plus L. So that limit can distribute across a sum. Okay. Second property that we get is that the limit as xy approaches x0, y0 of k, a constant, times f of xy is equal to k times M. In other words, this constant k can move outside of the limit if we would like first, and then we just take the limit of f of xy, which is M. So constants can move in and outside of limits with no problems, just like they always have been able to do. Okay, we also get that the limit as xy approaches x0, y0 of f of xy, g of xy is equal to M times L. In other words, a limit can be distributed over a product of functions. We get that the limit as xy goes to x0, y0 of f of xy divided by g of xy, then this is going to be equal to M divided by L, provided that L is not 0. Okay, and finally one more. We get that the limit as xy approaches x0, y0 of f of x, y to some power. Let's say that we raise it to the r over s power. Then this is just going to be M raised to the r over s power. Okay, so any fractional power that I raise that thing to, the limit can just move inside the power, and I can take the limit first and then raise it to the power. Okay, so basically all the rules that we already had for limits in 2 dimensions also apply to limits in 3 dimensions, and that's all we're really trying to say. So all the things we know about limits we can still use. Okay, let's do an example to kind of show how this works. So let's start. Let's find the limit as xy approaches some specific point now. Let's say it's approaching the point 0, 1 of x minus xy divided by x squared y minus x minus y. Okay, so we've got to kind of go back to the basics and just remember when we took limits to begin with, what was the very first thing we would always try? And that is, well, can I just plug in the point? And if I can just plug in 0, 1 and I don't get any division by 0, then we're done. We get our limit value. And so we should try that. So if I plug in 0 for x, notice the top just becomes 0. And on the bottom, I get 0 minus y. Well, y is 1, so I get minus 1, which gives me 0. But 0 is not division by 0. 0 is a number. That's perfectly fine. So I get my answer, and my answer is 0. Okay? Let's do another example. Let's find the limit as xy goes to 3, 4 of the square root of x squared plus y squared. Again, if I can, let's just plug in the point. Am I going to cause division by 0 by plugging in 3, 4 for x and y? No. There's no division by 0 going to be happening, so I can just go ahead and plug it in, and I get 3 squared plus 4 squared, which is the square root of 9 plus 16, which is the square root of 25, which is just 5. Make sense? So, the first thing that we would always do, and we still do it now, is we just try to plug in the point itself. And if we can plug it in and we don't cause any division by 0, it's great. We can just get the limit that way. So we should probably look at an example where we do get some division by 0 and see what we do. Okay, so let's try this one. Let's take the limit as xy approaches 0, 0 of x squared minus xy divided by the square root of x minus the square root of y. Okay, so now the first thing we might try is to plug in 0, 0. But if I plug in 0, 0, I get a 0 on the top and I get a 0 on the bottom. And that's not so good, we know. A limit is not typically going to give us 0 over 0. That's an indeterminate form. We don't like that. So the next question we typically ask is, can I factor this thing? Well, it doesn't look like I can factor the bottom, but I may be able to factor the top. So I get the limit as xy goes to 0, 0 of, on top I could factor out an x, and if I do, I get x times x minus y divided by the square root of x minus the square root of y. But x minus y up here, that's the difference of squares if you think of x as the square root of x squared and y is the square root of y squared. So let's rewrite. This is the limit as xy goes to 0, 0 of x times square root of x minus square root y times the square root of x plus the square root of y divided by the square root of x minus the square root of y. So the square root of x minus the square root of y cancels on top and bottom, and I'm left with the limit as xy goes to 0, 0 of x times square root of x plus the square root of y. And now the question is, can I just plug in zeros for x and y and not get division by 0 anymore? And the answer is yes. I can plug in zeros, and so I just get 0 times 0, which of course is 0. And so now all of the tricks that I know, multiplying by a conjugate, we can apply here, and we can potentially, we could multiply the top and bottom by the same thing, multiply by 1, combine fractions, all these different things that we've done before in 2 dimensions. We could now use the same tricks in 3 dimensions to find limits. Okay, the second thing that I want to talk to you about now is if we have limits in 3 dimensions, then we can also talk about continuity in 3 dimensions. So let's talk about continuity. And let's remind ourselves what continuity means. Sometimes we think about continuity as I can draw something without picking up my pen. Okay, that's kind of the simple way of thinking about it, but there's a better way to say it. And so let me write down the definition of continuity, specifically in 3 dimensions. A function f of xy is continuous at the point x sub 0, y sub 0, if a couple of things are true. First, f is defined at the point x0, y0, and 2, the limit as x, y goes to x0, y0 of f of xy exists. And 3, those two values need to be the same. In other words, the limit as x comma y goes to x0, y0 of f of xy needs to be the same as f of x0, y0. Okay, if those 3 things, so we have a functional value, we have a limit value, and those 2 values are the same thing. And that's what it means in 2 dimensions to be a continuous function as well, is you're defined at the point, you have a limit value at the point, and the limit value equals the functional value. So no real change here. Okay, so another thing that we had in 2 dimensions that we'll also define in 3 dimensions is what does it mean for a function to be continuous? This is continuous at a point, right? Continuous at the point. But we can also talk about what does it mean for the entire function to be continuous. So let me write that definition down for you. So definition, a function is continuous if it is continuous at every point in its domain. Okay, so for the entire function to be continuous, then it needs to be continuous at every single point in its domain. So it doesn't have to be continuous at points that aren't in its domain. It only has to be continuous at the points that are in the domain itself. Okay. So let's do a little example. So an example, let's show that the function f of x y is equal to, it's going to be piecewise defined as 2xy divided by x squared plus y squared if xy is not equal to 0, 0, and it's going to be 0 if xy is equal to 0, 0. Okay? Now, first of all, an interesting question. I need to finish writing the question, I guess. Show that that is not continuous at the point 0, 0. All right. Well, if you plug in 0, 0 to this function, you get 0, right? That's what the function says. You get 0. But the question is, are the points around that point 0, 0, are they close to 0? Or could they be kind of far away from 0? Well, the thing is that if this thing is going to be continuous, then it needs really to be getting close to 0 everywhere around it. So how am I going to test everywhere around it when I'm really working in 2 dimensions in the xy plane? Well, it's good enough for me to show that there are some places around it that are not getting close to 0. So what I'm going to do is I'm going to evaluate this function in the xy plane. So think of the xy plane for a second. Here we are, xy plane. And I'm looking at the point 0, 0. I'm saying, let's take some points that are close to 0, 0 and see if they're small. So what I'm going to do is let's look at just a little like neighborhood around 0, 0. And I want to take a specific path to 0, 0. And I'm going to call it a path that's along some line that goes through 0, 0. It could be any path. I'm just choosing a line path because it makes it easier for me. And then I'm going to say, well, what is that line? Let's say that this line is y equals mx. So what I'm going to do is I'm going to say, if I'm walking along this path and getting close to 0, 0, then m is my functional value, also getting close to 0. It should be, because I said if things are close to 0, 0, then their functional values should be close to 0. So what I want to do is I'm going to take this function f of x, y, and I'm going to evaluate it at y is equal to this function mx. So in other words, let's replace the y here with mx and see what happens. Okay? So if I do that, let me rewrite here. I have f of xy is equal to, evaluated at y equals mx is equal to 2xy divided by x squared plus y squared, and that's going to be evaluated where y equals mx. So now I'm just going to replace all my y's with mx's. So I get 2x times y, but y is mx, divided by x squared plus y squared, but y is mx squared. Okay, let's rewrite that again. So I get, this is 2m x squared divided by, notice that, okay, the bottom is x squared plus m squared x squared. So everything has an x squared, so I could cancel the x squared on top and bottom, and I get a 2m on top, and on bottom I get 1 plus m squared. So this is interesting, right? That what my value is as I'm coming in towards 0, 0, well, it really depends on the m, right? If m is 1, what would I get out of this thing? Well, if m is 1, the top would be 2, the bottom would be 2, I'd get 1. Now, is 1 close to 0? Not really. It's kind of far away. It's not like 0.0001. It's 1, a whole unit away. What if m were like 2? Then I'd get 4 over 3. That's even, I'm sorry, if it were 2, I'd get 4 over 5. That's 1. It's a little closer than 1 was, but it's not very close to 1. So what I'm seeing here is that this varies with my choice of m. So depending on what path I travel through the origin, so if I take one line, I get one value. So this maybe is y equals x, and so m is 1. And so the values that are close to of this function are going to be 1. But if I travel on a different path, like 2, then the values of this function are going to be 4/5. So what I'm seeing here is that it depends on what line I'm going through, what value I get out of my function. That when I'm close to the origin, and they're not all the same. So this thing is not going to be continuous at 0, 0. So the function is not continuous at 0, 0. Functional values exist for all these points, but the functional values vary, and as the functional values vary, they vary very close to the origin as well, and so they're not getting close to 0, and that's basically what we needed. Okay, so let's talk about what's called a two-path test. So a two-path test for non-existence of a limit. Okay, so if a limit doesn't exist, how do you show that it doesn't exist? Well, you really need to find two different paths on which you can approach that point that have different limits. And if it has two different limits in some sense, then it doesn't have a limit, because all the limits need to agree no matter what path you're traveling. Excuse me, had to sneeze. So let me write this down. If a function f of xy has different limits along two different paths as xy approaches x0, y0, then the limit as xy approaches x0, y0 of f of xy does not exist. Okay. So let me draw a picture of this just to show you. So let's say that I have a point in the xy plane. It doesn't really matter. And I want to know what happens as we get close to x0, y0. Okay. And I'm walking along one path, and I say, as I'm getting close from this direction, my functional value is getting close to 2. But as I walk at this point from this direction, the functional values are getting close to 3. Well, then I'm getting close to this path tells me the limit should be 2. The other path tells me the limit should be 3. Well, it can't be both of those, so it must not have a limit. So if you can find two different pathways to the point, which tells you that the limit should be two different things, then what you find is it must not have a limit there at all. Let's do an example of this so you can see kind of what I mean. So, quick example. Show that the function f of xy is equal to 2x squared y divided by x to the fourth plus y squared has no limit, as xy approaches 0, 0. Okay, so we have to choose what direction this thing walks along. So I can choose any path that goes through the origin. I just have to decide what path is going to be the most helpful to me. And what I see here is I've got some x squareds in my original function, and I have some y's in my original function. So the path that's going to help me the most, that will make this thing simplify a little bit, is I want to walk along the path y equals some number k times x squared. Now, what is that path? That is a parabolic path that goes through the origin. But I don't know what k is. So here's the origin. And let's say that k was equal to 1. Then I'm walking along the path of just my standard parabola. If k was negative 1, then I'm walking along the path of that parabola flipped. If k is equal to 2 or something, then I have kind of a stretched parabola that I'm walking along. So it just depends on what I choose for k. So in essence, I'm doing a lot of paths at the same time, walking along all these various parabolic paths. And you might ask, well, why did you pick a parabola and not a line? Just because the parabola is going to make things simplify better. You could use a line. But if it doesn't simplify, the line may not help you very much. Okay? So what I want to do is I want to look at this function, f of xy, evaluated where y is kx squared. And definitely your path, though, needs to go through the point that you're evaluating. And it does in this case. Okay, so if I want to evaluate that function where y is equal to kx squared, then I get 2x squared times y, but y now is kx squared, divided by x to the fourth plus y squared, or kx squared squared. Okay, we can simplify that a little bit more. And on top, I would just get 2k times x to the fourth. And on the bottom, I would get x to the fourth plus k squared x to the fourth. So all of the x to the fourths cancel, and I get 2k divided by 1 plus k squared. And now the question is, so it's saying that if I take the path kx squared, this is what I'm going to get out of the function. Okay? Now, what if k was 1? If k was 1, what am I going to get out as all of the functional values here? Well, if k is 1, then I'll get out as my functional values 2 over 2, which is 1. Okay? So what I'm seeing is if I take the path where if k is 1, then what I'm doing is I'm saying, okay, let's walk along this parabola to go to 0. So as I get close to this point 0, what are all of these functional values? Well, I said if k is 1, then I just get 2k over 1 plus k squared. If k is 1, this is 2 over 2, which is 1. Okay, so if I'm walking along this parabola to get to this point, the origin point, I'm going to get 1s all the way. So this limit, if it exists, it has to be 1. But what if I walked along a different path? Like what if I said that, let's say k was 2. If k equals 2, then I'm walking along a different parabola, a more steep parabola, to get to the origin. So I'm walking along, what am I getting close to? I'm get 2 times 2 is, so 2k over 1 plus k squared is going to be equal to 4 over 1 plus 4, which is 5, or 4/5. So if I'm walking along this path, I say, well, my limit must be 4/5. And this, the first one said the limit must be 1. So if it must be 1 and it must be 4/5, I'm in trouble. So that means that I've just shown that 2 different paths give me 2 different limits, so the limit does not exist. Okay? So I can say, so f of xy has no limit at the point 0, 0. Because along 2 different paths that I took, I got different limits. And a function can only have 1 limit at a point. Okay. I think you're ready to do some homework. Good luck.